Hello everyone, this is Mr. Chu again, and I would like to use this opportunity to go through some ideas about how to do the worksheet that you have in front of you. I thought it would be helpful for you if we go through the tips on how to solve the problem. So this is the worksheet I'm going through, in case you wonder, and I will go through some questions really fast because they are factual, and some of the questions that require more help, I'll go through them slower. So for 1A, you're supposed to prove that the wavelength of this is 1.89 eV. So you use the equation E equals to hc upon lambda. This is Planck constant, 6.63 times 10 to the power minus 34. This is speed of light, and this is the wavelength in meters. And you'll get this answer in joules. You have to convert it to EV. If you do it correctly, you should find that it's 1.89. B part 1, you're supposed to draw an arrow to show the transition. So once you have the 658, and it corresponds to 1.89 eV, you need to find the transition, and you have to be very clear whether it's pointing down or pointing up, because it's emission, so it should point down. So you should find the two energy levels that has a gap of 1.89. And you repeat the same for 1B part 2, you get all the other transition. You need to calculate the energy of each of them. 1C, explain why the lines get closer and closer towards the shorter wavelength. Now the clue and the hint is in this. So if you take a look at this tree, if I add another one, if you take a look at this 4 energy transition, can you see that the difference in energies are getting smaller and smaller? So think about what happens to the difference in wavelength between A, B, C, and D. What's the difference between, how would the difference between wavelength in D and C compared to the difference between C and B compared to the difference between B and A? So that will give you a hint on why it gets closer and closer. And think about this, where the lines get closer and closer, is it higher energy or lower energy? 2A, absorption spectrum, go and refer to my video for 7.1. 2B as well. 2C, one of the wavelengths in the absorption spectrum occurs at this. Same process over here. So go back to the video 7.1, you should be able to find the hints to do that. For 3A, you're supposed to find the number of protons and neutrons. I will leave you to do that because you have learned that in chemistry before as to how to find what does the 81 represent. So you got 81 bromine and 35. What does this number represent and what does this number represent? So you can find the number of protons and neutrons from there. 3B, how many alpha particles and how many betas are emitted together by this to form this? Now this one I'll go through with you, but I'll still leave some space for you to find out for yourself. So the way to do this is, if you have X number of alpha particles and Y number of beta particles, what you should do is to balance the top number and balance the bottom number. So by balancing the equation, there are two unknowns, two equations over here. You should be able to find the value of X and Y. That's for 3B. For number 4, the same thing. You just need to make sure that the equation that you write balances the top and bottom number. For number 5, A, showing the mass number, same thing, nuclear reaction. I'd like to focus a little bit more on 5B and 5C. So you're supposed to find the minimum energy to make this reaction occur. So to find the energy required to make a reaction occur, say for example you got X plus Y giving you A. Now in order for you to supply this, to find this energy, what you need to do is to take, if the fact that you need to supply energy means that this has more mass than this and this. So you take mass of A minus mass of X minus mass of Y times C squared. That would be the energy required. Okay? So sometimes it can be this, depending on the phrasing. The phrasing says energy required to cause the reaction, so it should be on the left side. If it is energy produced, it will be on the right side. So use the masses. Remember to convert the U to kg, and then the energy will be in joules, then convert it to MeV. What is the total Ke of the product? The same thing. In the reaction, the alpha particles have this. So the alpha particle, this is, if I were to rewrite the equation, energy of alpha plus the 14 plus alpha plus 14, 7 nitrogen, giving you 17, 8 oxygen plus proton plus Ke. So what you should do is to take energy of alpha, you convert everything to energy. So energy of alpha plus mass of alpha C square plus mass of nitrogen C square is equals to Ke plus mass of oxygen C square plus mass of proton C square and then you can find this one, given the mass of everything else. So the idea is really to convert everything to energy. It is also possible to convert everything to mass. That means you take this divided by c squared plus the mass of this plus the mass of this equals to the mass of this plus the mass of this plus this divided by c squared. It's simply this equation, whole thing divided by c squared. So you can look at it from the mass perspective or the energy perspective. It works both ways. 6a, you balance the equation, top and bottom, you should be able to find the answer. Energy release, same method, take the mass initial minus mass final times c squared. Remember to convert to kg, remember to convert to EV. Now number 7 is linked to 7.1, which I mentioned. You have to be very careful about what is the mass, what is the number of particles that is remaining versus the number of particles that has decayed. This is so important that I'd like to just run through again. Very, very important. So if I got n number of particles to begin with, after one half-life, this will be n upon 2, n upon 2. The decayed is 0 over here. This is undecayed, which is n. So decayed is n upon 2, this is n upon 2. After another half-life, this is n upon 2, n upon 4, n upon 4, n upon 2. So the one that is undecayed, okay, I got the other way around. So it should be the other way around. So after another half-life, what you have over here is n upon 4, n upon 4, n upon 2. So whatever that you have that has decayed is 3n upon 4, and whatever that has undecayed is n upon 4. So you must be very careful whether they ask for this or this, because it's two different answers. And sometimes they can present the ratio as in undecayed to decayed. For this one, undecayed to decayed will be 1. For this one, undecayed to decayed will be 1/3. And make a guess, what's the next one? After the third half-life, what is decayed? Undecayed to decayed is 1 upon 7. All right, and then 1 upon 15. And then you can see the pattern. Now, number 8. Two radioactive sources A and B have the same disintegration rate at the beginning. A has half-life of 1 hour, B has half-life of 2 hours. What's the ratio after 2 hours? Now, this is a very interesting question. So, activity, they have the same activity. Now, for this one, you need to have, okay, activity of A equals, activity of A original equals to activity of B original. And the half-life of 1 hour and for B is 2 hours. So after 2 hours, A final will be A original. After 2 hours, A will have gone through 2 half-lives, so it's 1/4. AB final will be equals to AB original times half. Why? Because source B has a half-life of 2 hours, and after 2 hours, it's only 1 half-life. So the ratio of disintegration from A to B, you can say that if you take this divided by this, you get half. So you do the same for number 8b, and you get the answer. Now, number 9 is very interesting. Number 9 is a question where it's actually something that is being used, a technique that is being used. So something originally that has 12,000 counts, the radioactive substance, is injected into a human. Now, after this radioactive substance is injected into a human, it looks a little scary, but actually it's a very small amount. Into the person, what happened is we have to assume that after some time, everything is distributed evenly throughout the whole system. So what happened is that after 30 hours, once the MQ is extracted and it has 0.5 disintegration per minute. So the half-life is 15 hours. Now let's take a look. After one half-life, it should fall from 12,000, original is 12,000, T equals to 0. After one half-life, if I don't inject it into the person, it's 6,000 altogether. After 2 half-life, which is 30 hours, after 2 half-life, the half-life is 15 hours, after 30 hours is 2 half-lives, it'll be 3,000. So this 3,000 will be distributed evenly throughout the person. The only difference is, I inject it into the person, then it starts to reduce. Over here, for easier understanding, say for example, if we keep it here, after 2 half-lives, it will have been 3,000 and then injected into the body to be distributed. So, if after 2 half-lives, if I can gather everything out, it will be 3,000 instead of 12,000. That's if I get everything out. But this everything, this 3,000 is distributed over the whole system of the blood, which is the total volume of blood. And this is equals to 0.5. And therefore, you can get the answer, which is 6,000. It's about there for normal human beings. Now, for number 10, I will not go through. I'll leave it to you to do it on your own so that you get the chance to practice without guidance. And you need to do so because in exams, you won't be guided. So I hope that these short tips of how to solve the problems is useful for you. If it is useful, I'll continue to do so in the future so that you get something, not just lecture, but also on tips on how to solve problems. And I think it's important for kind of a starting phase for you to solve problems with some form of guidance and some form of archive guidance. All right, thank you. Have a good day.